Hello? Can everyone hear me? Yeah? Okay, cool. Great. Hello, welcome back. It's Friday. Does anyone have any fun weekend plans? Let's do fun weekend plans. My roommates are going skiing. Who's doing something fun? Oh, my roommates are not going skiing. What are you doing? Wow, great answer. Yay. Okay. So today,
Can I make an announcement?
yeah. Oh yes, Fischer has a very important announcement.
Very important announcement. This is great. This is big news for the program. Can I get a drum roll, please? We have the end.
Yay.
Shout out IS&T for taking care of this. There's just a little bit of miscommunication on our end. But as of like an hour ago, VM should be online. Setup instructions are up to date on the website. Go ahead and try those out. If you're like on Mac, click out the posts if stuff doesn't work, but everything should be good to go. I have not tested this myself yet. I haven't had the time. Go ahead and give it a spin. Let me know if stuff is broken.
Yes. And also, if you're worried about due dates, don't. If you're a Mac user and like, yes, Lab 1 was due yesterday, you didn't get Altium until today, I don't expect you to have completed it by yesterday, quite obviously. Just get it done as soon as you can. For design reviews Tuesday, if you don't get the Bluetooth speaker schematic done, that's okay. We'll push a design review to another day, and like we'll work it out, but we'll get back to you because we don't know how many people it is, so we can't really tell you a schedule right now. But just try to get it done as soon as possible. Let us know if you need extra help, office hours, etc., or whatever, and reach out to us. Now, okay, so this lecture is on motors and motor control. So you might be asking, like, why are we talking about motors and motor control? It's a PCB design class. So there's a couple of you in track 2 who are actually designing motor controllers. And motors and motor control are honestly a really, really good case study on how to design PCBs. Some of like the most, there's a lot of things to consider when you design PCBs, especially with motor controllers like that. We're not going to get through all of those considerations today. Our goal is basically going to be to tell you like how does a motor controller work? Why is it complicated? Like why is it a difficult problem? And what are some of the problems you have to solve along the way? And yeah, so this is, the other thing I'm going to try to do is this is a motor controller from Ben Katz. For those of you who are not familiar with him, he designed the Mini Cheetah. His motor controllers are used very widely in a lot of dynamic robotic systems, and I have some of it over here that I'm going to demo in a second. But we're going to go through what are the parts of a motor controller, why are they on there, so it's a little bit of a design intuition building on why motors do things. And also, motors are cool. They're really cool. They're absolutely wild. So we're going to talk about them for a little bit. But before we get started, I have a fun demo, which is these legs. And these are 2 Mini Cheetah legs. And basically what we have is we have 3 brushless motors on each leg. And they're communicating with each other. So this board over here reads the position from each of the legs. It reads the velocity that each leg is moving at. And it tries to tell the other leg to do what this leg is doing. It's called teleoperation. So if I move this leg, give me a second and reset that. Sometimes it does. Of course, it works perfectly every time until I start talking. There we go. Here we go. So if I move this leg moves. Now the other cool thing I can do with this is because it's setting a torque here proportional to the difference between the position joints, if I smack this leg on the table, I can actually feel it. I can feel the force that the table is pushing back on the leg with. So you guys can come play with this later. But yeah. So for now, I'm going to start very basically with basic model of a motor. For those of you who are not super familiar with it, I'm going to call it the 4-magnet model of the motor. I don't think that's its official name, but that's what I'm going to call it. And basically, a motor has 2 major parts, right? A thing that is stationary and a thing that spins. The thing that is stationary is called the stator. The stator has a bunch of wires on it, produces a magnetic field, and then the rotor has permanent magnets on it and it spins. And this is what it kind of looks like up here. So I have a stationary, is red north? Yes. Sorry. I have a stationary north pole. I have a stationary south pole. And then, in the middle, I have a magnet that rotates. Here's my rotation center. So how does a motor work, basically, right? So if I just do this, right, where are the forces on this magnet coming from? Which way is this thing going to try to rotate? You're making a motion. Yes, this way, right? Because north attracts south, south attracts north, north repels north, south attracts south. Now, this is going to be fine for about, 3 milliseconds until I get to this position. Right, now I'm here, and what direction are my forces? Right, it's like pulling like this, right? I have no torque. And then, if the motor starts to spin this way, what's going to happen then? It's going to try to come back, right? It's going to try to put a torque back this way. So what I need to do is I need to switch this pole from a south pole to a north pole, and this from a north pole to a south pole as the rotor passes this like axis. I'm going to call it A0 for now. And then when I do that, the motor can continue spinning. When it comes here, I need to switch it again. When it comes here, I need to switch it again. Does that make sense? So instead of me going in there with my motor and replacing the magnet every time it rotates 180 degrees, which would be a very difficult way to control a motor, there's a couple of ways. Yes, how do we do? There's two types of main motor. There's two major motor types, and how we do that is through either a brushed motor, where it's a little bit hard to see what's happening here, but it's better than me drawing it on the board. So essentially, those black lines are a positive and negative wire, right, from my power supply. And those two little rotating things, do you see those rotating things that are contacting and uncontacting those two wires in the middle? I have a pointer. I have a pointer that doesn't work. Right in the middle of that, can everybody see what's going on there? Those are connected to the coils of the rotor that's moving. In a brushed motor, the coils move and the magnets are stationary, because what happens here is if I send power one way through a coil, right? I have a coil. Current's going one way, the magnetic field goes this way. If I switch the direction of the current, magnetic field goes the other way. So those little things what they're doing is that's a positive and negative of this coil, and then there's a positive and negative from the power supply, and what that little mechanism in the middle is doing is switching the voltage back and forth like this. Does everybody see how that's working? This is called a brushed motor. Those little things are made of, what are they usually made of? Graphite, carbon graphite. Those are brushes. And basically what you can see is happening here is that there's physical mechanical contact that needs to occur to make this like motor work. So there's like friction in these motors and they're not as efficient. So we came up with, well, not we, someone came up with an alternative called a brushless motor. A brushless motor has no brushes, and there's many types of brushless motors. There's like, you can have 3-phase, you can have 6-phase, you can have 2-phase, you can have as many phases as you really want. But the most simple type of a brushless motor is a 3-phase brushless motor, which is essentially what happens is you have these 3 coils, and as I vary the voltage to each of these coils, I can like make this magnet rotate and change the direction of the field without having to like have anything physical in there switching directions of magnets. People see how that works? Is anyone confused yet? Okay, great. Okay. Where'd you go? Okay. Now, obviously, this kind of system, if I just apply a voltage to it, the motor will spin, because the field switching is happening inside the motor itself. A system like, well, I got rid of it, but a system like a brushless motor, I need to, as an engineer, apply signals that allows me to switch the motor field around and around and around, right? It's not going to do it itself, which is why all brushless motors need to be run through a motor controller. And that's what the ESC is doing. Like if you've ever played with a drone, you have like the little motor and you have the thing that connects to the motor and then it goes to the battery pack. That's what the ESC is doing. Okay, so I'm going to briefly, I know some of you, a lot of you probably have already seen this model before, but I'm going to like just go through it quickly to make the point, and then we're going to get to more detailed control of electric motors. But basically, inside a motor, this is the most basic model of a motor. And to clarify, this is a DC motor brushed. We're going to talk about a brushed motor for a second, and then we're going to get to a brushless motor, because brushless motors get a little bit complicated. So this motor is this one on the side with the brushes that switch back and forth. Stop. There we go. So in a DC brush motor, like this thing over here, if I turn it on, I can observe some phenomenon. If I apply a voltage to it, and I vary this voltage, let's drop the voltage, speed goes down. As I increase the voltage, speed goes up. Now I'm going to apply increasing friction. You're not going to be able to see this on the power supply because it's a little bad, but as I apply more and more friction, speed goes down, but current increases. The current reading increases, but as I change the voltage, the current reading doesn't really change. So why would that be? So let's look at a basic model of a motor. Here are the terminals of my motor. This is called the armature of my motor. That's just a term that we call for the two terminals coming out of motor. These are the two wires. Positive wire, negative wire. This is the inside of my motor. I have a resistance. Where does this resistance come from? Anyone tell me? The brushes and also windings. It's a wire. Wires are, like, in real world, never perfectly ideal. So I have a resistance. Then I have, anyone take 6002? All right, we got a couple. There's a lot of dependent voltage sources that you go through in 6002. This one I'm going to call a speed-dependent voltage source. And I'll get to that in a second. This connects around this way. This voltage source, basically, a motor is an electromechanical transducer, right? I put in electrical energy, I get mechanical energy out, which means what also must be true? If I can put electrical energy in one side and get mechanical energy out the other, what can I do? I can do the reverse. I can put mechanical energy in one side and get electrical energy out, right? That's how we generate electricity. So what's happening here is due to a whole bunch of magnetics, just mute. Due to a whole bunch of magnetic properties and the fact that I'm spinning magnets around coils and things like that, if you think back to 802, I can generate a voltage by spinning the output of the motor. Yeah? So this voltage source is a voltage that is proportional to the speed of the motor, speed being the angular speed omega, through a constant called the back EMF constant. So I'm going to say voltage is equal to KB times omega. This is a number you measure. You put motors on a testing rig, it will tell you the back EMF constant, it'll tell you the torque constant, all this kind of stuff. The other thing I can say about a motor is, so actually this tells us a couple things. If I apply a voltage V to the input terminals of the motor, what's going to happen, right? I'm going to start, actually, sorry, let me say this first. If I have a current passing through the motor, the torque at the output of my motor, also through physics, if we like go through and do like all the calculations and figure out like where the forces are and that kind of stuff, the torque we found is directly proportional to the current going through the motor through a constant called the torque constant of the motor. Again, something we measure. Is everyone good so far? Voltage is KB omega, torque is KTI. Everyone good so far? So if I apply a voltage to the motor, and this is not spinning, what's the voltage here across this system if it's not spinning yet? I've just started. 0, right? There's no V equals 0 initially. So that means there will be a voltage difference across this resistor of voltage V. If I have a resistance R, the current V, wow, that was terrible. V equals IR, so V over R equals I. So I'm going to get a current going through the motor, so I'm going to get a torque output of the motor. The motor has some rotational inertia J motor. What's going to happen to this inertia? I'm applying a torque to an inertia. What happens when I apply torque to inertia? It spins, it accelerates, right? It's going to accelerate. Is it going to accelerate forever and ever and ever and ever and ever? What's going to happen? Billy? So as this motor speeds up, right, it's going to create an increasing voltage here as it gets faster and faster and faster, right? Until what point? When is this motor going to stop accelerating? When is current going to go to 0? The voltages are equal. I have an input voltage. I get a back EMF of KB times omega. When the back EMF voltage is equal to my input voltage, sorry, I really should have annotated that a little bit better. I'm sorry, guys. V input equals V back EMF. So V input will equal, speed will be V input speed will be the input voltage over my back EMF constant. So what's happening in this power supply, right, is as I vary the voltage, the motor is speeding up to catch up to the voltage that I'm giving it. If I give it 12 volts, it will operate at a certain speed. If I drop that voltage down to 5 volts, it'll operate at a lower speed, but no matter what, at steady state, my current is going to be 0. If I apply a torque, if I apply friction on the output, I see a current increase because the motor is trying to counter the torque produced by the friction of my fingers. Does that make sense? Yeah. And this is kind of where the torque speed curve comes from, right? We can kind of see that in this case. So the torque speed curve of a motor, okay. Torque and speed. So at a given voltage, let's say V equals 12 volts, the max speed of my motor will be plotted as a point on this axis, right? Yeah? Anyone confused? The maximum torque of my motor, if I have V equals KB omega. Now remember, this is the input voltage. Torque is equal to KT times I. This is the input current to the armature. The torque will be an intercept on this axis. And as I speed up the motor, the torque will linearly derate until it achieves this point. Now in lecture 1, I also told you that the torque speed curve is dependent on voltage. Right? Remember that? So if I increase voltage, what happens to this curve based on these equations? Right? Do we see where this increase in voltage changing the torque speed curve comes from now? I kind of just said it lecture 1, but does this start to make sense? Now, the other thing I said in lecture 1 is you'll see a saturation torque on some larger motors. Essentially, what that means is if I get to a point in my torque speed curve where I'm reaching magnetic saturation of my material, the torque speed curve, basically what you're doing is you decapitate the torque speed curve, right? You say, like, I can't achieve torques higher than this, so I will decapitate it. So that's where the flat line in the torque speed curve comes from. Really, it is a line that's moving up and down until you hit saturation. Does that make sense? Cool. Okay. So this is the torque speed curve for a brushed motor. Does it change for a brushless motor? Anyone? Remembering that they're really fundamentally the same device. We're just changing how we're switching the magnetic field, right? No, the torque speed curve shouldn't change, right? Because it's still fundamentally the same, like it's still a motor. It's going to have the same physical limits. It's going to have the same model. If I spin a brushless motor, it's also going to produce a voltage. The only difference between how you calculate a torque speed curve for a brushed motor and a brushless motor, where's my white chalk? Here it is. So a brushless motor has a motor controller, the 3 phase wires that go to the motor, and then a DC input here. What we're doing is saying when you switch the field, right, back and forth, essentially what this is doing, this like section in here, is like the electrical equivalent of the analog brushes that are switching everything back and forth, right? That's where the field switching is coming from. So what I'll say is if this is my output shaft of the motor, I will draw a large box around the motor controller and the motor and say this torque speed curve will apply based on the voltage and current going to the input of my motor controller and the torque speed coming out of my motor. Does that make sense for everyone? Cool. So this should also tell you something else. It should tell you how efficiently we can switch the field in an electric motor determines the performance of that motor, right? Because if I'm providing power into this device, and this device, any losses I see at the output are really coming from how well I can switch that field in there. In a brushed motor, all the losses are coming from the fact that I have these 2 mechanical things that are rubbing against each other back and forth. Okay. Any questions so far? Yeah. So, okay, that's a good question. What dictates saturation torque was the question. So if I look at an inductor, right? A motor is essentially the coils of a wire wrapped around a piece of magnet or a piece of metallic, is an inductor essentially, right? So I can have a piece of metal in here, let's say it's iron, and I can have a coil of wire wrapped around it, right? This is kind of like one of the things that's going on inside my brushless motor, right? Sorry, I pointed to the slide. There's nothing on the slide, but like, you're following me so far? So inside here, what's happening is when I pass a current through this wire, right-hand rule, it produces a magnetic field inside the solenoid that looks like this, right? So the way, with increasing current, this iron core in here, what's happening inside the iron core is there's all these little tiny like magnetic domains. This is not the greatest explanation of this. There's a very good explanation of this linked in the lecture notes on how magnetic saturation happens. There's 2 videos from the guy who does Veritasium, whatever. Veritasium, yeah. The guy who does those has a really good video on how this works. But essentially what's happening, right, is as I pass a magnetic field through this, all my little magnetic domains, all the little magnets inside my material, if it's a ferromagnetic material, align, right? At some point, I've passed so much magnetic field through this that all my little domains are in this direction. And they physically cannot be more aligned, right? So if they are physically as aligned as they possibly can be, all of my magnetic field is saturated in the sense that like I can't align the core more to produce more magnetic field. Does that make sense? Okay. And that's where this comes from. Now, of course, this is dependent on the magnitude of electric field that I'm passing through the iron, which is why really you only see magnetic saturation on like the larger size. Like you won't see it on something like this when you read the torque speed curve, but you will see it on something like this, which is a very high torque density motor. Anything else before I get to field-oriented control? Yeah, what's up?
So is the dominant resistance in the brush motors actually from the brushes and not the wire itself?
It's primarily from the brushes, yeah. But the resistance that determines how much torque actually, I shouldn't say that. Never mind. Yes. Did I see a hand over here? No? We're good? Cool. So, what is field-oriented control? Field-oriented control, so the question becomes, right, like we know how the, sorry VMs, I need board space. The question becomes, right, how do I make a brushless motor spin? Because it's very obvious in a brush motor that it's physically switching field back and forth with the brushes, and it will keep going round and round and round and round until I tell it to stop. But I'm designing a motor controller, which means to know how to design the motor controller, I need to know what this thing needs to do to spin, right? So if I look at a motor, like this one, I can pass this around if people promise not to drop it. If I look at a motor, essentially I have a whole bunch of coils, and I have a whole bunch of magnets. And these coils are, in a brushless motor, situated on the stator of the brushless motor. They don't move. And the permanent magnets move. There are many types of brushless motors. We're not going to get them into too many, knocking into the table over here. Not getting into too much detail right now, but basically this is an in-runner motor. And what this means is the magnets spin inside the stator. That is being passed around as an outrunner motor because the magnets spin around the stator that sits on the inside. And a brushless motor has 3 input phases, phase A, phase B, phase C, and that's how we control the direction of the magnetic field inside the motor. Now, any motor, when it's engineered, has an order of phases that's very important, and they design these order of phases so that we can follow this simplified model of a motor. Essentially, this model has phase A, phase B, phase C, and if I rotate it and change the phases in order and then connect them all together, I will get this model. But this model will always apply to that model in the sense that, like, based on the geometry of how I designed this, it's really just a bunch of these on top of each other rotated. So if I apply the model to this one, and let's say I'm saying, like, with this model, I predict a certain amount of torque. If I multiply it by how many times I've rotated, I can predict the torque of, like, a bunch of them superimposed on top of each other. Does that make sense? That was kind of a little bit weird, but did I confuse anybody? I'm getting a few blank stares. Okay, my main point is I can simplify any motor from that into this simple 3-coil, 1-magnet system. So my question now becomes, how do we do the thing, right? And the answer to this is field-oriented control. Field-oriented control is a technique for controlling brushless motors where what you're essentially doing, so this is a donkey. I promise it's relevant. But if I have a donkey and I want the donkey to move forward, there's the classic scenario where I put a carrot in front of the donkey and the donkey follows the carrot. This analogy, I realize, makes more sense after you see what's happening inside the motor rather than starting by explaining that. But basically, what I'm trying to say is, like, I have a magnet that's rotating around. That's the stator. And the magnetic field I want to produce needs to pull that magnet around the motor, right? So I'm going to start by defining a few coordinate systems. This is A phase, this is B phase, this is C phase. All the phases in a motor, how it works is essentially you have like the A wire input, the B wire input, the C wire input. You have all the coils, and then at the end, all these three things are connected together at this point. That's called the star node. That's just how an electric motor looks inside. I'm going to erase this for now, but we'll come back to it later. I'm only erasing it for like cleanliness of the board. So I have these three solenoids, and I have a magnet. I'm going to go north, south. So the first thing I know, right, is that these are all, I can simplify these to magnetic solenoids, right? So I'm going to pass currents IA, IB, oh, sorry, that's going to, and IC through this system, which, because it's a solenoid, we know through right-hand rule will produce BA, BB, BC magnetic fields. Yes? I'm going to simplify these magnetic fields. Since magnetic field magnitude will be proportional to the current magnitude going through solenoid, I'm going to speak of this for the rest of the lecture as a current field, IA, IB, and IC, just because that is the notation that is chosen for field-oriented control. It is essentially the same thing. When I say I'm passing in a magnitude of current, that is the magnitude of the magnetic field. It's just with some constants, right, and geometry. So the first thing I can say is I want to figure out, right, I am passing all of these currents through my motor. What does that mean in terms of what does the magnetic field look like inside the motor? So what I'm going to start with is by defining a coordinate system called the alpha-beta coordinate system. This is the alpha. That's a really terrible alpha. This is the alpha axis. This is the beta axis. And what I'm going to do is I'm going to put the first solenoid, phase A, on the A axis. On the alpha axis. At a 120 degree offset, I'm going to put B, and at another 120 degrees, I'm going to put C. How did I come up with these angles? We start with, these angles come from physical motor geometry. You start with, this is the simplest model of the motor, and when you design more complicated motors, you make sure your motor design follows this initial topology, basically for analysis purposes. If we did anything more complicated, we'd need to change everything we're doing here. So for example, if I had two-phase field-oriented control and I had the phases oriented this way, I would have different math. But the way you get to the answer is still the same. So then what I'm going to do is say, like, okay, I know that the magnetic field, because I'm going to assume, right, like I have the stator and the rotor, and there's a tiny gap in here of size delta. This gap is so small that what I'm going to do is I'm going to say I'm going to simplify this to vector addition. I'm going to say field A, oh, I should have used a different color for that. Bad Addy. Field A, field B, field C. And to get the total field in the electric motor, or like total magnetic field in the electric motor, what can I do to these three vectors? Add them. There's a field going this way, there's a field going this way, there's a field going this way. They're vectors. I can add them, right? So, very simply, I'm going to add these vectors onto this coordinate system. So, my I alpha is going to be equal to IA plus what? It's okay, it's Friday. IB times the cosine 120 degrees plus IC times the cosine 240 degrees. I beta, alpha is not along the beta axis at all. It's completely perpendicular, so I can ignore the the phase current of A. IB times the sine 120 degrees plus IC times the sine of 240 degrees. And what this basically says, right, if I pass three phase currents through this motor of magnitudes IA, IB, and IC, I can project them onto this 2D coordinate system and get I alpha and I beta as these values, right? This is called the Clark transform. Clark was actually a very cool person. Clark was she was a MIT, she was an MIT alum, first woman to deliver a paper at the American Institute of Electrical Engineers. She's from here. Very cool person. She did this. You should Google her. She's done some pretty awesome things. But yes, so the Clark transform basically says I have three currents. How do I determine the magnetic field in a stationary reference frame inside my motor where one axis is pointing across, pointing to phase A? Yeah? Anyone lost? Great. And this is the output of what we will call the forward Clark transform. Forward is a key word here because we will get to inverse later. Inverse is technically more useful, but I'll explain why in a minute. So this helps in the sense that I can now write one magnetic vector, or one vector that determines what is the output of all three of my phase currents, right? I've simplified all three of my phase currents to one vector, which is great. But I still don't know how to apply this vector to the fact that my motor is now spinning like this in a weird fashion. So I need to bring those two things together. So, where's my blue and my red? I'm going to define, let's start with the alpha axis and the beta axis. I'm going to define another coordinate system because we're engineers and we love coordinate systems. North, south. So, what color should I use for this? Let's do different, sorry. Let's define an angle. Now, let's assume in my physical motor, I know where the A-axis is physically. Like, let's say I make a little mark on the motor saying, like, this is my A-axis. And then I know where the north pole of my motor is because I assembled it. So I can say, like, this is my north pole. And if I put a position sensor or some other thing on this motor, I can find this angle theta. Can we agree on that? Does anybody not know that we can find this angle theta? Okay. So let's assume we can perfectly measure theta for the moment. Turns out that is actually a very reasonable assumption, but we'll get to that later. I can now say I have defined, what colors did I use for, oh, yeah. Okay. Well, sorry, purple. From my previous work over there, I defined an I alpha and an I beta, and this is the magnetic field from my motor that my stator is producing, right? I alpha and I beta. This coordinate system that I'm going to label as, oh, I don't want to mess this up. This is D, and this is Q. This is the D-axis. This is the Q-axis. Is a rotating coordinate system that rotates as my motor rotor spins around. Yeah? So now what I'm going to say is, no matter what the angle theta is, I can project my stationary magnetic field onto my rotating coordinate frame. Can I do that mathematically? Is it physically possible? It's possible. It's annoying, but it's possible. So what I'm going to go ahead and do that is I have I alpha, I have I beta, and let's say this is my d-axis. This is, oh God, this is theta, and this is a 90-degree angle. Vector projections. Yay. We all love vector projections. Okay. So I'm going to say ID is going to be what? I'm projecting the vector. ID is going to be I alpha times the cosine of theta plus I beta times the cosine of 90 minus theta. Yes? That's how I project a vector. What is the cosine of 90 minus theta? Sine. Great. You guys are quick. I had to Google it before lecture. Ooh. Well, with me so far? And now I can do the same thing. Let's stay here. If I do, is that what I want to do? That is what I want to do. Alpha, beta. This is my q-axis. This is the angle 90 plus theta, yeah? And because here's my perpendicular d-axis, and this is a coordinate frame that is rotated by theta, this angle is theta, yeah? So that means IQ is equal, to remember math, I alpha, sorry, this will, times the cosine of 90 plus theta plus I beta times the cosine of theta. Yeah, did I do that right? Okay. So, sorry, this is IQ. I don't know if I said IQ or I alpha, but this is IQ. IQ is then equal to I alpha cosine 90 plus theta is negative sign. IQ, and ID. Yes? This, is there an E at the end of park? There is not. This is called the park transform. Now you're probably like, great, that's a lot of math. Why is this useful? So basically, yeah, we'll stick with this. Basically what I know, right, is I have a magnet that's rotating around and around and around. The D-axis that I have defined is an axis that goes along the direction of the magnetic field of the magnet. The Q-axis is an axis that goes perpendicular to the magnetic field of the magnet. So if I remember all the way back to here, colors, sorry. D-axis, Q-axis. So if I want ideal torque production, because if this moves around, my torque gets smaller and smaller and smaller and smaller until it hits 0, right? What I want to do is take this magnetic field that I'm creating and keep it perfectly perpendicular to my magnet as it spins around. Yes? This is the reason we do all this math. Because now what I can do is I can say, I need to apply a magnetic field around my Q-axis. So let's set ID equal to 0, because putting current that way doesn't get me anything for now. There's a situation in which it does get you something. We're not going to go over it in this lecture, but if you're interested, it's called field weakening control. What I'm about to show you is field-oriented control. Field weakening is a subset of field-oriented control, but for now, ID is 0 because we just want torque. IQ, I want a torque-producing current. So based on this, and based on the fact that this is equal to 0, and I can measure theta, I have a system of linear equations, right? I can find I alpha, and I can find I beta. Now from there, I know I alpha, and I know I beta. Oh no, I have 2 equations and 3 unknowns. The world is about to explode. What can I do? Give up, great answer. No. What can I do? It was really subtle. I said at the beginning of the lecture, I don't think anybody remembers, but if it helps, I also forgot. Fischer had to remind me. So, where's my brushless motor model? Here it is. Inside my motor, there's only 3 wires coming out of my motor, right? There's not 6. If you look at the motor, there's only 3 wires coming out. If you look at an actual brushless motor, somebody has it. There's only 3 wires coming out of it. Where did the other 3 go? What we did is we tied them together here into what's called the star node. This is what so the A phase, B phase, and C phase wires that come out of your motor are one side of each of the 3 solenoids, and the other side I've tied together inside the motor, physically, twisted them together, soldered them together. This is called the star node. But let's look at my star node. Where's my, yes, I want to do this here. If I look at my star node, I have, what's coming into my star node? Look at this, look at this, look at this, look at this. What's coming into my star node? Current. IA, IB, IC, sorry. So I have 3 currents adding at a point. What rule do I use? KCL, Kirchhoff's current law. 0 is equal to IA plus IB plus IC. I can now solve my system of equations. Sometimes you will see this denoted instead of 0 as I0. All I0 means is the 0 current vector. It just means all three are adding to 0. So if you go and Google the Clark and the Park transform after this, then if it says IA plus IB plus IC equals I0, it's just telling you all three currents add to 0. And this is the third part of my Clark transform that allows me to solve the system of equations. And I can then get what current do I apply to IA, what current do I apply to IB, what current do I apply to IC. So all my motor controller has to do is apply a current here, here, and here. Yes? To get my motor to spin? So how do we do that? Fischer is about to talk about it in a minute. I will say a couple of things real quick. So we can measure these currents. Actually, I don't want to do this. I'll just confuse you. Yeah. Actually, it's better. I think it's better if you explain your thing, and then we get back to how to measure the currents and things like that. But does everybody understand the point that if I apply, let's assume I can apply 3 perfect currents to this system, I can get any vector that I want. And the magnitudes of those currents determines the direction of the field. And the magnitude of the field determines the total torque. Cool. Let's take a 5-minute break. Let's come back at, is it 2? And then what we're going to do is space vector modulation, which is how you actually apply currents in a physical motor controller. And that's the design part of the class. Okay. All right, shall we? Okay. Is that can people hear me okay? Cool. We're going to get started real quick. Okay. We're going to get started real quick. The place we're going to start at is. Sorry about that. Okay, we're going to start with that same motor model with the 3 coils program. And we're going to try and build some intuition as to what exactly we need electrically in order to drive this. We spent a lot of time talking about motor currents, and the purpose of the motor controllers that we want to build, especially for a lot of Type 2 people, is to generate those currents in the motor. But we're subject to the limitations of physics, electronic components, and what we can practically fabricate. So this is going to be a bit of how we would actually practically implement this. Cool. So let's try to build some intuition real quick. We have this ABC motor configuration, right? And then there's a magnet that's spinning on the inside. If I was to take the current through one of these coils, let's call them A, B, and C. I also take the current through one of these coils and plot it as a function of time. What shape would I expect it to be? I heard it a little bit louder. Sinusoid? Sinusoid? Is that? And yeah, that's exactly correct. As the magnet is passing around and around, we want this to vary as a sine, right? We want it to have some periodicity to it as the magnet comes back around. And we will get a curve that looks about like this. And we will call this the current through phase A, IA. Excellent. Okay, so we know this. Any guesses as to what the current through B is going to look like?
Sinusoid but shifted.
Exactly. By how much?
By 6 degrees plus.
60 degrees plus, you said?
Maybe.
You're close. You're very close. It's going to be 120 degrees because there's a 120 degree angle between these 2 coils, physically in the motor. Each coil is doing the same thing. They're just spaced a little bit, in space. So the current is going to vary a little bit in time because the magnet's going to start out here and then it's going to rotate, and then get here, right? Does that make sense? Does it seem like reasonably intuitive? Cool. So we'll draw that as this. And this will be the current. I need to find a better way to attach this. Okay. If I do that, is that too loud? Or does that sound okay? Okay, great. Cool. So then we'll do the same for phase C. Excellent. So these are all motor currents on each of our phases. And we need to generate a circuit that is capable of producing these things. Well, if we want to generate a current across something, we need to put a voltage across it first, right? In order to get electrons to think about moving through the coil. So I'm going to draw us a circuit that'll do that. Let's say that we are making a motor controller for like some kind of like vehicle or a mini cheetah, a robot, something. And it's going to be battery powered. So I'm going to draw a battery here. Here's the plus side, here's the minus side. And that's going to go across here. Voltage on top is going to be called V plus. Voltage on the bottom is going to be called V minus. And then what I'm going to do is I'm going to put in two switches. One here, one here. And then I'm going to care about what happens at the midpoint here. We call that point A. Now, we have two switches here, each of which has two states, on and off. So that means that for the whole thing, there are how many total states? Just blurt it out. 4. 2 and 2. Cool. So can we, let's go ahead and like enumerate them and see what's useful. So I'm going to call this switch 1 and switch 2. And let's say switch 1, switch 2. And let's say we start off with switch 1 open, switch 2 closed. What's that voltage on A going to be? This is open, this is closed. V minus, exactly. All right, let's do the same thing. Closed and open, what's it going to be? Just yell it. V plus, excellent. What if I leave both of them open? It's floating. What that means is this has no connection to the rest of the circuit here. And it's not something that we want to do in the real world. The reason being is that inductors that are inside of our motor, because we have these big coils, don't appreciate it when they're like disconnected from the rest of the system. If you're curious about why exactly that happens, feel free to talk to us afterwards or like ask us. But it's basically because the magnetic fields in here don't like to change, and if we isolate it from everything else, the inductor will like blow up these transistors if we were to implement it as such. But we're getting ahead of ourselves. Okay, what happens if we close both of them? Say that a little bit louder?
Shoot through it, it destroys the controller.
Well, yeah, but this is a battery too. So we short out a battery, we will have boom. And that's a bad thing, we want to avoid that. So given this, we have 4 states. 2 that are going to be kind of useful for putting voltage on our little point here. And then 1 that's kind of dangerous and maybe a little bit useless. And then 1 that blows everything up instantly. Honestly, that's about our luck. 2 states are useful, 1 blows everything up, 1 is kind of useless. Okay, so we have this. And we're going to focus on these 2 states for now. I'm going to consider these to be the only like permissible states for this circuit. Does that seem okay with everyone? Cool. So we're trying to build a circuit like this in order to control a motor like this. And we have 3 points that we would like to interact with, and this circuit will give us 1. So let's just go ahead and copy this over. And now, we'll call this the B point. And this will be the C point. Make it a little bit better. C. And we're going to connect these to the A, B, and C points on our motor over here. And by switching the configuration of these switches, we can put currents into our motor coils. And we're going to do that by changing the voltage that's on them. Does that seem legit so far? Cool. Sweet. So I'm going to erase these so we don't get confused. But for this, we have 2 states that each of these little bridges can occupy. We have 2 states and 3 bridges. How many total combinations does this get us for like states of this entire circuit on the whole? Anyone? Anyone? 2 states times 2 states times 2 states gives us 8. Exactly. So let's go ahead and write that out. I'm going to call the state when this one is closed to be like the positive state, and the state when this one is closed to be the negative state, right? Because we're putting V plus on something or V minus on something. So let's go ahead and write out what these do. And we're gonna number them as well. Cool, so let's enumerate. And let's go ahead and give them all numbers. Cool. Does that seem legit? That's all 8 possible states that we can have. So let's go ahead and take the first state, and let's connect all of our switches here to be V minus. So we'll get V minus on A, V minus on B, V minus on C. What will that do in our motor? What's going to happen to the currents inside of our motor here when we do this? Yeah?
No current.
Yeah, it's going to do literally nothing, right? Because all these are at the same voltage. There's just going to be no reason for any electrons to like bother going through the coil at all, right? Because the voltage here is the same as here. No current's going to flow. Great. So, nothing. Is there another state that we could create here that would give us the same net effect? I heard it somewhere over here, a little bit louder. Did you have it?
8.
Yeah, 8, exactly. Yeah, if we connect everything to V plus, we get like nothing useful, right? There's no voltage. These are the only 2 states that'll do this. Everything else is useful. So let's start out with state 2. A and B are minus, C is plus. So we'll take this, connect it to minus, and this to be plus. Actually, if you don't mind, I'm going to redraw this in a slightly different orientation. Do that, and then there, and then there, just to match my notes, sorry. Okay, perfect. All right, so we put A and B as minus, and then we put C as plus. Which direction will our magnetic field inside the motor point? Just show me with your arm, like just point which direction, where's it gonna go? If we have a plus here, it's gonna go up through here. So it's gonna like point straight up, right? Like due north. So since it's a magnetic field, it's a vector, and I can move those vectors around. So I'm gonna put it here. Let's make it a little bigger. And since this is the vector that's produced by state 2, let's label it 2. Okay, let's play the same game for the rest of our states. For state 3, we put A and C at V minus, and then turn on B. Which direction is this going to make our magnetic field go? Again, just like give me a little like thing with your hand. Yeah, it's going to go this way. Or, excuse me. Yes, this way. Cool, so that'll be state 3. Excellent. And then now let's consider state 4. So minus plus plus. So we put negative here, plus positive here, positive here. This will put the magnetic field in this direction, right? Because we have current coming in this way and out through this coil. And then that will be state 4. And then 5 is A plus. These will be minus, and that will push current down through this way, right? And now we get 5. And then can somebody tell me what 6 is going to do? If A and C are both positive and B is negative, what will this one do? Exactly. We'll go here. So that's 6. Okay, and then the last one is 7, so A and B will be positive, and then C will be negative. Which direction does this go? Straight down. Yep. Okay, cool. Excellent. So we can steer the field in 6 different directions, right? Based on the 6 possible options that we have for our switches here, we get 6 directions to put the field in. Cool. This is a technique known as 6-step commutation. Let's write it here. The reason for this name is because it has 6 steps, as we just saw. There's 6 valid states. And we call it commutation because that's just the process of flipping a magnetic field inside the motor. For the brush motors that we have up here, and also the super big yellow one that's out in the lobby, those have those carbon brushes to do this for us. But here we're using switches for it, and we get to pick the state of those switches. Cool. Any questions on this thus far? Excellent. Okay. We can represent this as a hexagon. If you'll forgive the crudity of the drawing. And we have all of our states along it. There's 2, 6, 5, 7, 3, and 4. Great. And we can also represent the dead states on this diagram as well. We'll put 1 and 8 at the center because they don't really put field in any direction. So this encompasses everything. Cool. Let's say that I have this lovely diagram. Great. I've done some simplification. I've worked this out. Okay. Wonderful. Let's say that I want to start spinning a motor that has a magnet at the center of it, right? This is our rotor, and then here's our stator. If I want to start rotating this way, could you tell me the combination of states that would be required in order to make this move clockwise? Well, let's say that we're starting out with state 2. What's the next one? 6, and 5, then excellent. Next. 4, right? Fabulous. So that's wonderful if I want to go clockwise. What if I wanted to go counterclockwise? What would I do, starting from 2? We'll put the magnet in the same spot to begin with. What's the first state? 4. Then, and, yep, followed by, and then 6, and then we're back to 2, right? These are the exact same sequence. We've just done them in the opposite order, right? So this is actually how we pick what direction our brushless motor is going to go. We pick the order that we change between steps in. Excellent. However, we can actually improve on this just a little bit. When we have our magnet in here, we can only put field, from our stator, we can only put field along this direction, this direction, this direction. And that's totally fine for when our magnet is exactly in one of these orientations. But for this, remember that the part where the configuration of our motor that generates the most amount of torque is when we have if we go back to our 4-magnet model, if these are our stator magnets, this is our rotor magnet, this is the configuration that gets us the most amount of torque, right? Because the norths are repelling as hard as they can, the north-souths are attracting as hard as they can, and then the souths are repelling super hard, right? This is what gets us the most amount of torque. So what we want is the magnetic field of our rotor here to be orthogonal to the magnetic field in our stator. And this is the field we can control. This is the one we can't. These are permanent magnets. These are electromagnets. And that's the whole reason why we did all of the Clark and Park transforms before. It was just so that we can figure out exactly how to make those fields be perpendicular all the time. But does this setup allow us to do that? We have 6 states. Does our magnet always lie in one of these 6 states? You're shaking your head, no, why not? Well, magnets have mass, right? They can't instantly snap from here to here to here to here, right? It takes a little bit of time for it to move around and rotate, right? So if we want to maintain this condition where we're getting maximum torque and the most out of our motor, because we have them to produce force, in order to maintain this condition, we actually want to steer our magnetic field at that 90 degrees to the magnet at all times, right? We have to maintain this condition here. As the whole thing rotates, as the rotor magnets rotate, we want to rotate the stator magnets with it, right? So this whole condition here is preserved. So does that make sense thus far? Cool. So if we can maintain that condition, we produce the most amount of torque, we're getting the most out of our motor, yippee. But we can't do that with our 6 steps that we have here, because these are discrete, but the rotation of this is continuous. So can anyone think of a way where we could somehow try and get in between these states somehow? Let's say my magnet was here, right? And we want to maintain that perpendicular field condition. So what I want is to have let's say we're rotating this way. What I want to have is a north pole here and a south pole here, but I can't get that, right? Because I want the field inside of my stator to point this way, but I can't get that. The best I can do is 4 and 3, right? What can I do with 4 and 3 in order to get something that's kind of in between? Any ideas? Huh? Yes, exactly. We can alternate between the two. If I wanted to produce a field that was this way, how much time would I spend in 3 and how much time would I spend in 4? 50-50, right? I'd spend just as much time in 3 as I would in 4. And the technique that lets us do this is called pulse width modulation. And honestly, it is one of the greatest concepts to ever grace electrical engineering, and deserves its own platform. So when we engineer motors, we get a choice for we can choose how fast they run. And so we have a rough idea of how fast this magnet's going to be spinning, right? In the case of a mini cheetah, those magnets might actually be moving well, depending on, that's a bad example. So when we spec the motor, we'll know how fast this is running, right? So what we need to do is oscillate between 3 and 4 quickly enough to the point where the motor doesn't notice, right? We have to run it electrically a little bit faster than we run it mechanically. So here's what that looks like. Let's say that I want to produce a vector that's between 3 and 4. Or actually, any arbitrary signal. That'll be fine. Let's say I want to produce a sine wave. Right? What I could do is I could have a digital signal that occurs at some frequency. Something like this, maybe. And what I'll do is, depending on how large this is, I can change the width of the digital signal. This is better explained with a picture than it is with words, so I'll just go ahead and draw it real quick. Here we have a large value that we want, so let's go ahead and make this be like super wide. Over here we have a value that we want to be a little bit lower, so we will go ahead and do something like that maybe. Sorry. Let's do it less strong like this. That'll be a little bit less, and then we'll have a pulse here, and then when we get to our next pulse, it'll be of even less length, right? And then as we try and get to 0, this one will just be flat, and we can do the same trick for what's going on over here. So we'll have a pulse that's just a little bit wide, and then another pulse over here that's even smaller. And this will also be flat. And we can play the same trick and copy this over here. Sorry, that diagram did not come out how I wanted it to. Does the concept generally make sense? I can explain again if it's a little hairy. Yeah, what's up?
The heights are all the same, right?
Yes, sorry. Sorry, let me just go ahead and move it on because I confused myself a little bit. All right, so we have a digital signal, and we want to get an analog one out. And the way we're going to do that is just by changing the width of the pulse, so that when we average it out over some range, we get the analog signal that we want. So over here, we'll have maybe a larger pulse width. Sorry. Have a small pulse width, and eventually gets a little bit longer, and then have a really long pulse width as we get towards the center of this curve, and then it shortens up a little bit, goes back down, and it gets really small, and then we eventually go to 0. And we can play the same trick over here. Sorry, does this diagram hopefully make a little more sense? Okay, cool. Sorry about that. All right, so this is called pulse width modulation. And the signal that we're trying to get up here is called the modulation index. And that basically just tells us like how wide do we make these pulses when it comes time to do PWM. And the frequency that we output these pulses at is called the switching frequency. And it's something that we get to pick when we design our motor controller. The higher, the better, usually. Because if we output more pulses, we can have finer control over the curve that we're producing. We get a better approximation of it. The higher, the better in terms of signal quality, but it also costs us something in order to produce a higher frequency signal. And we'll get to that in a little bit. But just know that in order to produce a better signal, we need a higher switching frequency. Are we almost at time?
Yeah.
Okay.
I guess I was going to say if people have to leave at 2:30, then feel free to go, but you could continue to proceed.
Sure. Cool. I will speed ahead a little bit though. Okay, so we have a control frequency here, and that lets us ping pong between states. What that effectively lets us do is it turns our 6-step commutation into something a little more advanced. We have the same hexagon, but now we can actually move between states. So that turns into a circle that's inscribed on the inside, and now we can have our magnetic field vector point in whatever direction that we want. It can point here, it can point there, it can point there, and that'll follow the exact magnetic field of the rotating magnet inside the rotor. Does that hopefully make sense? Cool. Okay, so we'll do that, and excellent. So we have our circuitry here, and all this will do is take a modulation index and turn it into waveforms like this. Now the question is, how do we generate that modulation index? Like I can now change my magnetic field to point whatever direction I want, but I need to know how. And this is where the transforms discussed earlier come and like help us out a bit. because what we want to do is what we want to do is maintain this field condition here. And from before, we saw that we can generate a D and a Q axis here. And we want to maintain said condition along the Q axis. So from before, we had a set of transforms that will take us from IA, IB, IC space to alpha, beta coordinates, and then from there to D and Q. And this is great, but now we actually want to run in the other direction. We have a field condition that we want to maintain by putting everything on the Q axis, putting all of the current that we put into the motor on the Q axis so we get the most amount of torque out of it. And we want to work backwards through our transforms in order to find what how much current we should put through. And we can control this current by the modulation index. So we just run these in reverse. And so when we made the point earlier about like a forward Parkin-Clark transform, it's important because now we're about to do the inverse. So when we do that, we end up with a system that looks a lot like this. We have a voltage that we want to put on the Q axis, the voltage that we want to put on the D axis. This is inverse Park and Clark. And then from here, got our modulation indices. This goes out to our bridge. And then from this, we have our motor. Excellent. So we're most of the way to a motor controller, actually. We just want to know how to, we have the math to go from a desired voltage on the Q axis, which is going to turn into a desired current on the Q axis. Once we actually apply it to the motor, we have that, we can determine our modulation indices from those, and then we're good to go. What is the one thing that we do need for these transforms, though? The one parameter in all of our modeling? Theta, exactly. And theta is our rotor position, right? Like, that's just a knowledge of like where our magnet is inside of the motor. So we need that. Adi said that we could assume that we know it. But in the real world, when we go to build these, how could we determine what that value is? We need like some kind of a sensor, right? What kind of sensor could we use? Yeah?
Use that solenoid since it's a magnet.
Huh?
You could use that solenoid.
We could, and that's one special type of control called sensorless. That one has a couple caveats that we want to avoid for things like this. So yes, that's totally valid. And they also do make some special coils that are used for detecting like just position. Those are called resolvers, and they're an option. So, yeah, let's write down our options for position sensing. We have resolvers. And if you're on race car or a solar car might use them, I'm not entirely sure. We use these to control our motors there. What's the other option for figuring out position control? Yeah?
Encoder.
An encoder, exactly. And the way those work is just by having a wheel that has a bunch of like teeth cut in it, and then that passes in front of a little laser. And when the laser beam gets cut, we can detect that, and we know that we've like moved over by a step. Those are super popular. Any other ideas for what we can do here? Yeah?
Potentiometer.
We can. Since that's a mechanical thing, like we go back to the problem of having like stuff rotate against each other. So yes, but we have to pay for it in terms of like friction. So we don't see those too often in the real world. Yeah? Yes, you can use Hall effects. And what a Hall effect sensor does is it just detects whether or not there's a magnet in front of itself. And so we sneak those into our motor in some clever places, maybe like here, here, and here. We can actually use the rotating magnet inside of our rotor to tell us where it is. These are usually a digital thing. They tell us like, hi, there's a magnet in front of me, or no, there's no magnet in front of me. As a result, the estimate that you get from them is like not the best quality. So these give you like a very discrete idea of where your motor is, just like we had a very discrete idea of where we want our motor to go with 6-step commutation. So these are the way to give you the best estimates. So that value of theta that we put into our transforms jumps all over the place. The encoders are a little bit better, usually have some good resolution. They're relatively cheap nowadays, and they'll give you a far better estimate of your position. The actuators up here have a special type of encoder in them, called a magnetic one, but that's what makes this possible. And then resolvers are like the creme de la creme, super fancy, really boutique solutions that make sense when you're dealing with like large motors for like race cars and whatnot. Cool. However, there is one option that we haven't discovered yet. I'm guessing. And basically, this is kind of a popular thing that you'll see with like, especially like quadcopter motors, is that you can actually just guess where your motor is, and then just like hope that you're right. What this means is like we can play the game where we rotate our magnetic field and like turn it. Then it goes here, here, here. We can play this game and just keep rotating it, and just assume that the rotor will follow. This actually works for like quadcopters because they don't have a lot of load on their output, right? It's just a propeller going through air. So as long as we don't go too fast and like rotate our magnetic field too quickly, then we're good to go. We like don't break anything. Our motor is happily able to keep up, and we're okay. That lets us get away with not having any like sensor on the motor shaft, but only in some conditions. Does that make sense? Cool. That is called open loop speed control because we don't have any feedback on it. We have no idea how fast we're actually going. And so there's a feedback loop, but it's left open. As soon as we put some kind of sensor on this, it becomes a closed loop system. So this is going to be our motor position data. Excellent. Once we put this in here, it goes from open loop to closed loop, exactly. So then what this does is we can put a voltage on it, and then we have an estimate of what's actually happening, and then we're okay there. We can also put in a little bit of extra circuitry to like monitor what's going on with the rotor position itself, and see like, okay, is the rotor actually spinning at the speed that we want? If the answer is no, then maybe we turn up or down the voltage that we're putting on the Q axis. Cool. We also, like, since we're trying to produce torque, we don't put any voltage on the D axis. If you do, Adi mentioned it earlier, but if you put non-zero voltage on here, you do something called field weakening. And that's a special trick. So I don't know if you can see that. That's a very special trick that you can use to like get like extra speed out of your motor at the expense of like burning some power. But cool. Okay, so we have all of these circuits, and like this is generally what goes into a inverter or motor controller. Once you build them out, there's a couple other practical considerations you have to worry about, but you end up getting a system that looks a lot like this. This has a couple extra moving parts on it because sometimes what we want to control is the force coming out of the motor, the torque. In the case of like the arms over here, I wanted to have the system such that like when you push it, it pushes back at you. Like we care a lot about force in that case. And so when Addy put this together, when Addy put it together, he used a kind of control called current control. So we actually are monitoring directly the amount of current going into the motor coils. And we have some extra circuitry on here that does exactly that. So you can also hack on some current sensing equipment, which actually is on the next slide. Yep. This is the cross-section of a chip from Texas Instruments that does a lot of, well, basically all of this math for you. And it has a little thing built in where there's these little like resistors here that are in the red boxes. And when we put a current through resistor, that makes a voltage that we can sense. So this lets us figure out how much current is actually going through the motor. And that's quite useful for when we want to control the force that's coming out of the motor directly. And that enables really cool applications like this. Cool. So to tie this back to what this means for PCBs, we basically have to consider the circuit elements that are making this happen. We have these switches up here that are moving our voltages around how we want. These switches, as I've drawn them on the board, are like these nice, lovely on-off things. But if we wanted to have a switch that we could control, what kind of part would we use? Transistor, exactly. And since it's the real world, transistors aren't perfect, and so they have a couple of problems associated with them. But despite that, they're what everybody uses for building motor controllers. So, a couple problems with them. If we have a transistor, it's not a perfect switch. It has some resistance in it. And so if we try and put all of the current for our motor through that switch, what's going to happen? It has some resistance. We're putting current through it. It's going to heat up, exactly. So they get hot. So you have to think a lot about thermals. There's two ways that they heat up usually. They heat up a little bit when you turn them on and off, and that's called a switching loss. And then there's a little bit of penalty that you pay once it's actually turned on and you have current running through it, and that's called a conduction loss. I'm not going to go into how to calculate these or use them. We're just telling you things that if you're making a motor controller, you should be cool and know how to calculate so that you know if it's going to melt on you or not. So anyway, we produce a bunch of heat through these mechanisms. We have to get that off the board because we're making these on PCBs. One way that we can do that is with heat sinks that are built into the board itself. So if you remember from Wednesday, we have this nice fiberglass sandwich here that has some copper that lives on top. And copper is a really good conductor of both electricity and heat. So something that we can do is when we put our transistors on top of this thing, we can have a big layer of copper underneath that pulls all that heat away. So if we have a big sheet of copper underneath our transistors, then that'll help it dissipate the heat. So you end up with these big flat planes that are on your board that'll take care of that for you. We can also use the other side of the board to dissipate heat as well. If we put a bunch of vias through here, the vias, as we saw, are made of copper, right? So those will also conduct heat down and then out and then into the air. So if you're making a motor controller, look at some reference boards out there. You'll see this a lot. It's very common. Cool. We can also reduce our losses a little bit by putting parts super close together. If we don't have a lot of copper that's separating our parts between here and here, this copper has resistance to it, and we're putting current through it, so it'll also heat up. We put all of our parts super close together. We don't have to. There's not as much resistance in the connections between them, so then you get a little bit of you get some thermal savings there too. So you'll find that stuff, when you go to make motor controllers, have like these big planes with parts on it that are like super tightly put together. Cool. We can also increase the amount of copper that we have here. We can use a thicker layer as well. This is an option you can specify with the factory making your boards. So this is called like the weight of the copper. A higher weight of copper means that they put more ounces of copper on your circuit board, and it's thicker, can wick more heat away. Cool. The other big consideration we have to worry about when we're making boards like this is isolation. When we're making a motor controller, let's say it's for like a car or something, does anyone remember how high the voltage those battery packs are from what Addy said? Or if you're on a vehicle team, what voltage is your battery pack?
400 volts.
400 volts. Cool. So you have in the case of the race car, we have a 400 volt battery that we are wiring directly to this motor controller. But we also have a bunch of tiny little chips on it that are performing all the math in order to make this whole thing work. Those tiny little chips don't like 400 volts. They won't appreciate a 400 volt battery just being right on them. They will blow up. The first motor controller I made, I burned a hole in my desk because I accidentally put 90 volts onto a tiny little Arduino, and it just blew the board literally right in half. It was kind of gnarly, and I was scared. Don't have it happen to you. So we care a lot about isolation. And we want to keep circuits, we want to keep the high power stuff separated from the, want to keep the high power stuff separated from our lower level logic. So we have to worry a lot about clearance between things. So if we have some part of our board that is all low voltage, and some part of our board that's all high voltage, we want to keep these in two separate regions. We don't want to put high voltage stuff over here, we don't want to put low voltage stuff over here. And we usually care a lot about the region between the two. Sometimes we want to make sure that no signals move between here. So sometimes we'll actually just cut a hole in the board itself to physically isolate these two parts of the circuit. Sometimes you need that for super high voltage stuff. For the motor controllers that y'all will be building, we're not going to let you build anything at 1,000 volts or anything like that. So you won't need this, but you will see it in the field. But you will also need to calculate, instead what you'll do is just have an invisible boundary between the two sides of your circuit, and you'll want to make sure that even though there's no hole in the board, you want to make sure there's enough clearance between the low voltage side, the high voltage side, and we have some calculators and design tools on the website to help you figure out exactly what that is. Cool. Last thing that we have to worry about is electromagnetic interference. So this all matters for making sure that electrons don't physically jump from here to here and ruin your day. But that's not the only way that we can have things transfer, right? They can transfer through conduction directly across it, and that's called conductive EMI. But we can also have stuff transfer wirelessly, and that's called radiating EMI. Whenever we connect to a motor, we usually have these big long leads that connect to it, right? And each of these is actually perfect to function as an antenna for whatever wishy-washy current goes to our motor and back. So if we have these big antennas that are super long and next to a bunch of other sensitive electronics, say inside of a vehicle or a mini cheetah or whatever you have, those will radiate out into the rest of your stuff and can cause problems. So the way you mitigate this is with a couple of different techniques. Sometimes you'll see these parts called chokes that are put on your signal lines, and what those do is just try and snub out any anything that your wiring receives from the antennas that are broadcasting noise. So chokes are an option. And then there's also Faraday cages. If you're in track 1, you'll actually see this. On the Bluetooth speaker, there's we have a microcontroller called an ESP32. We'll talk about it a little bit more next week when we give a rundown on the Bluetooth speaker for track 1 folks. But we have that microcontroller has like a Wi-Fi and a Bluetooth module built in. Those are wireless, and you don't want interference from the rest of the circuit messing with that. So they actually put a big metal can over the whole thing to make a Faraday cage so that nothing escapes. It doesn't block everything, but it blocks enough to be useful, and so you'll see that upstairs. So, cool. That's about all we've got for you today. For all the track 2 people making motor controllers, if you have questions, please let us know. Piazza, email, we're happy to answer questions, and yeah, anything else you got to say?
Sorry for going so over. Motor controllers is a large topic.
Yeah, there's a lot of stuff going
we
on.
can cover, but yes.
Cool. Sweet. Thanks, y'all. Have a good weekend.